7C. Let's start talking about synapses. A synapse is the whole junction, the whole neighborhood where two neurons almost meet. And those two neurons are referred to as the presynaptic neuron and the postsynaptic neuron. All right. Some synapses are from axon of presynaptic to dendrite of postsynaptic. Some are from axon of presynaptic to cell body of postsynaptic. Far fewer are direct from axon to axon. Those that are from axon to dendrite are called axodendritic. Those that are from axon to cell body are called axosomatic, and those that are from axon directly to another axon are axoaxonic. Oh, and certainly a synapse between one neuron and an effector is also a potential, a possibility. Maybe I shouldn't use potential in this particular chapter. Okay, in the next slide, here we're depicting axosomatic. Here we're depicting axodendritic. And those are the scenarios that we're most often expecting, okay? Whereas much less common, axoaxonal. I just put a G in there. Nope. And now, okay, let's back up. Axoaxonal. Woo! I've been lecturing all day, so maybe I should stop. And yet, I don't intend to. Some synapses are electrical. Most synapses are chemical. Okay? An electrical synapse occurs when neurons or neuron-like cells are joined directly together, so that they're connected. They're actually sharing cytoplasm. And the intracellular junctions that allow them to do that are gap junctions. Electrical synapses allow communication to be very, very quick, but also poorly regulated. There aren't as many steps to interfere with. So it's not as easy to interrupt, for instance, an electrical impulse along electrical synapses. And having electrical synapses in certain places allows those organs to act as, and we'll run into this term in 242. Oh boy, do I even remember how to spell this? Syncytium? That looks wrong. I have to double check. Syncytium? SYNCYT. Oh, okay. Looks funky when I write it, but okay. Functional syncytium. If an organ is a functional syncytium, then even though it's comprised of different cells, the cells are acting as one unit. Okay, so the best example for that is the heart. Okay, where all the gap junctions that we're referring to are in those intercalated discs. Okay? But again, most synapses are chemical synapses. I'm on slide 5. And therefore, feature a space between presynaptic and postsynaptic neuron, and that space is called a synaptic cleft. Okay? A chemical synapse is comprised of presynaptic neuron plus that space. I'm going to run out of room. Let me write this elsewhere and smaller. Maybe don't use cruddy handwriting. Okay, maybe I still will use cruddy handwriting. Maybe there's nothing or no way around that. Presynaptic neuron, synaptic cleft, and postsynaptic neuron. Okay. And really it's the axon terminal of that presynaptic neuron. The surface of that axon terminal. And either the soma or the cell body, the receptive surface of that postsynaptic neuron. Okay. Well, if there's a space between these two neurons, then how are they going to communicate? The presynaptic neuron sends neurotransmitter molecules into the synaptic cleft, and mounted on the receptive surface of the postsynaptic neuron are presumably matchy-matchy receptors for that neurotransmitter. Okay? Just as our cells package so many other things internally in almost bubble-like containers that are called vesicles, so do neurons place their neurotransmitter products into vesicles. Those vesicles will fuse with the axon terminal surface and therefore exocytose neurotransmitter, but we'll come back to that. Okay. Next slide, 6, the synaptic cleft. This space here is the synaptic cleft. Okay. That makes this our presynaptic neuron and this our postsynaptic neuron. Okay? Because there's an interruption between the two, a space between the two, this is a far more controllable mechanism. We can interrupt this mechanism. We can throw a wrench into these works, okay? Neurotransmitters aren't going to pass directly from one neuron into the other. All right, next slide. Well, what do I want to do here? Yeah, I'll just zoom in. Okay, this is really cool. So, this is plasma membrane actually of a presynaptic neuron. In other words, this is axon terminal, okay? And embedded in the plasma membrane is this protein that acts kind of like a twisty tie, okay? And here's our vesicle, okay, with neurotransmitter inside. And in the plasma membrane that establishes this vesicle is another twisty tie. And when these two twisty ties come together, they twist together and spread the plasma membrane of, well, the plasma membrane of the cell, but also the membrane of the vesicle apart, and thereby allow neurotransmitter to be emitted. Isn't that cool? I love it. oops. Okay, next slide really zooms in on the synapse, okay? And again, the synapse is really this whole shebang, the whole neighborhood. It's not just the cleft. It's not just an axon terminal. It's not just a dendrite or a soma. It's the whole neighborhood, okay? And what we're seeing here are lots and lots of vesicles inside the cytoplasm of the presynaptic neuron. What's inside these vesicles? A neurotransmitter. Those neurotransmitter molecules get dumped out into synaptic cleft, okay? And if they find a matchy-matchy receptor, they bind to that receptor. They do not travel through these channels. No, 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 no. What travels through these channels? Ions. Ions. But not the neurotransmitter. Okay? We'll come back to this part. Oops. Where did my pen go? Oh, did it die? Of course it did. Oh. Despite that loud bang, I am totally okay. All right. I think we're ready to move on to the next slide. All right. Let's talk about different types of receptors, especially if they're associated with ion channels. Okay. Different type. Sorry. It's been a long day. When neurotransmitters bind to that matchy-matchy receptor, the matchy-matchy receptor might be an ionotropic receptor. It might be a metabotropic receptor. Okay? If it binds to an ionotropic receptor, then what it binds to is also going to act as an ion channel. That's actually what we've been using as our model thus far. Okay? But another possibility is that the neurotransmitter molecule binds to a receptor that is not itself an ion channel. Instead, that receptor is within the cell, coupled with a friend, and that friend is a G protein. When the receptor is bound to the neurotransmitter, it activates or excites the G protein. The G protein then in turn activates or excites other molecules in a chain or cascade. And at one point in that cascade is a separate molecule that acts as ion channel. Okay? Now you might wonder, why would we have both of these mechanisms in our bodies? Why kill this bird twice? Well, this is actually one of the reasons why, in this chapter in particular, I've started to bring up the idea of controllability. Okay, metabotropic mechanisms, whether we're talking about neurotransmitters or not, they have more steps. They're more involved. There are more players in this particular play. Okay, and therefore there are far more places where the process, the mechanism can be interfered with. There are far more steps, therefore there are far more opportunities for control. We have, therefore, more metabotropic mechanisms in our bodies than we do ionotropic mechanisms. Okay? And that will come back to haunt us in 242. So kind of keep those, even if you can't remember the words ionotropic and metabotropic, keep those ideas handy. Okay? Now, in the next slide, I've made a table for you because you're spoiled, and I've started to fill it out. You fill out the rest. Precious babies. All right, next slide. Again, again is our overview. This time it's a little more labeled. Notice that traveling along the axon is an action potential. Hopefully you're not surprised. And when that action potential arrives near the axon terminal, look at what it encounters. Look at what it encounters. Some voltage-gated calcium channels. In response to that voltage, that action potential, these voltage-gated calcium channels open up. Calcium floods into the axon, okay? And that's what acts as the signal to tell these vesicles to go find their matchy-matchy twisty ties. Isn't that cool? Like it. Okay? Once vesicles fuse with plasma membrane, they're going to release neurotransmitter into the synaptic cleft. And then those neurotransmitter molecules can bind to, in this case, ionotropic. That's what's shown, ionotropic receptors. But probably more likely, metabotropic receptors. Okay, some kind of matchy-matchy receptor, which either starts or stops the postsynaptic neuron from releasing its neurotransmitter product. All right, next slide. What did I want to say here? Oh, just reiterating, which is funny because this just came out of my mouth. Graded potentials can be excitatory or inhibitory, whereas action potentials are always excitatory. Okay? And then also, I wanted to address what happens to neurotransmitter molecules once they're in that cleft. Sure, they bind to a receptor, but are they always bound to that receptor? Are we always going to be turning on or turning off that postsynaptic neuron for the rest of our lives now that neurotransmitter has bound? No. Three things could occur. It's possible the presynaptic neuron can take its neurotransmitter product back up. All right? It's possible that the neurotransmitter molecules would be sitting around long enough to be degraded by the many, many enzymes that we have in our bodies. It's possible that neurotransmitter molecules will simply drift away, diffuse, which still means that eventually they'll be enzymatically degraded. Okay? So those are the sort of fates, if you will, of neurotransmitter molecules. The synaptic cleft is really the only portion of of a neural pathway that applies any kind of delay. That's right. It can delay a neural impulse by as many as 5 milliseconds. That's amazing. All right, next slide, which is 14, I think. Postsynaptic potentials. How can a neurotransmitter create graded potentials that can vary in strength? Action potentials don't vary. As long as threshold is met, maximum is reached. Okay? But graded potentials do vary in strength to reflect the strength of stimulus. Okay? How do they do that? 2 major characteristics. How much neurotransmitter, how many molecules of neurotransmitter are secreted, and how long that neurotransmitter molecule stays put. Okay? Again, graded potentials can be excitatory or inhibitory. Unfortunately, there's this abbreviation used in your textbook, EPSP, which stands for excitatory postsynaptic potentials. It simply means that a graded potential excites the postsynaptic neuron. IPSP stands for inhibitory postsynaptic potentials. It simply means the graded potential inhibits the postsynaptic neuron from secreting its products. Okay, so I really want you to focus here. Hopefully that's clear. Next slide. Summation of graded potentials is possible. Summation of action potentials is not. And you might already be thinking math. Addition. Oops. Okay. It is possible to add together or sum multiple graded potentials. Okay? So, for instance, let's say that we've got a weak graded potential that is not strong enough to allow an action potential to reach threshold. Okay? Well, what if we have multiple weak excitatory graded potentials occurring at the same time or in the same general area? Yeah, they will add together, if you will, and are much more likely, therefore, to bring about an action potential past threshold. Okay? Summation may be temporal, meaning we have two graded potentials occurring on the same neuron, on the same postsynaptic neuron, near each other in time, or they may be spatial. Two or more graded potentials occurring on the same postsynaptic neuron, close together in space. Okay? Oops. There we go. Temporal summation. We might have an excitatory graded potential, and before it can degrade, another excitatory graded potential is triggered and therefore adds on to the sort of waning effects of that first one. Spatial summation, we may have many receptors activated simultaneously, therefore producing multiple excitatory graded potentials which can add together. Now, the reality of synapses is more like this. These yellow dudes are just glial cells, but all of these blue dudes, those are axon terminals, presynaptic axon terminals. Isn't that crazy? It's just covered. It's like coated. These are chemical synapses, and at this scale we can't tell, but the axon terminals are not actually touching the dendrites and soma of this postsynaptic neuron. Very cool, though. Next slide. 18. At least 50 different neurotransmitters have been identified. Most neurons make at least two different types of neurotransmitters. Okay, so that means that not only can we turn on or turn off via excitatory or inhibitory graded potentials, but there's even more variety allowed because a neuron may be able to produce this or that. A neuron may even be able to produce this and that. Okay? And that means a single neuron has a lot of influence. Okay? The most studied, the first to be identified, and therefore the best understood neurotransmitter is acetylcholine, which is very commonly abbreviated capital A, capital C, lowercase h. Okay? Acetylcholine is the neurotransmitter that is released from a presynaptic neuron that is a synaptic cleft away from a muscle cell. Okay? This means autonomic nervous system. Okay, which hopefully makes you think better. Okay, some of the autonomic neurons will secrete acetylcholine. Some central nervous system neurons will secrete acetylcholine. Other types of neurotransmitters, to name a few, just a few, include the biogenic amines, into which dopamine falls, norepinephrine falls, epinephrine falls. Wait, aren't norepinephrine and epinephrine hormones? Yes, if they're in the blood. If they're not in the blood, then they're not hormones. Neurotransmitters and hormones are just types of cell signals. And the only difference is that hormones are born in the blood. Okay? All of these biogenic amines are made from or derived from the amino acid tyrosine. Okay, these three. Serotonin is another biogenic amine, but it's made from the amino acid tryptophan. Okay? Histamine is another biogenic amine, but it's made from the amino acid histidine. How many times have I asked students which amino acids make which biogenic amine? Never. Never. Okay? But I would like for you to know that biogenic amines tend to play roles in our emotionally driven behaviors, as well as our sense of a biologic clock. Okay? Some of our autonomic, and motor is of course redundant, neurons will secrete biogenic amines, especially norepinephrine. Okay? And often if we have an imbalance, an excess or a deficiency in a biogenic amine, it leads to mental illness. Next slide is 20, I think. Okay, again, neurotransmitters can be excitatory, they can be inhibitory, okay? And, which means they can either lead to depolarization or hyperpolarization, okay? And a really nice way to kind of showcase that is to talk about acetylcholine, okay? Acetylcholine may have an excitatory effect. It may have an inhibitory effect. It depends on what receptor it binds to, okay? My iPad died in the middle of that last slide, 20? We're like 2 slides away from done. Yay! Anywho, acetylcholine, when it binds to a receptor on a muscle cell, it is excitatory. Whereas when it binds to a receptor on, I shouldn't say a muscle cell. When it binds to a receptor on a skeletal muscle cell, it's excitatory. When it binds to a receptor on a cardiac muscle cell, it's inhibitory. Wow. Okay, let's talk about linkages between neurons. Okay, there are lots and lots of possibilities as to how neurons can be linked, and when they are linked, we tend to call that linkage a neural pathway. Okay, and the most common neural pathways are diverging, converging, reverberating, and after discharge. pathways or linkages, okay? A reflex arc, by the way, is usually a chain, okay, that includes a sensory neuron, an interneuron, and a motor neuron. Sometimes a reflex arc will link a sensory neuron directly to a motor neuron, but usually, or often I should say, there's an interneuron in between, okay? Whereas these diverging, converging, reverberating after discharge, these are more complex circuits, okay? Diverging, we're going to start at one or few neurons and synapse with so many others that we end up really amplifying the message. Whereas converging does pretty much the opposite. We're going to start at many neurons and influence few, or even possibly one, okay? Reverberating, we're going to see a linear pattern that feeds back on itself. And we'll actually encounter this one again in 242 when we're studying the respiratory system, because our breathing rhythm is controlled by reverberating circuits, okay? And then an after discharge circuit, it's kind of a combination between diverging and converging, because it first diverges and then reconverges. And we tend to have this layout when we want to bring about lasting responses. And, take that with a grain of salt, lasting with respect to the nervous system, not in comparison to the endocrine system, all right? So these linkages, I think, are the last slide that we have in chapter 11.